Hi, I am Marife Delos Santos from Bachelor of Science in Information Technology second year. And today I want to discuss the chapter 6, which is the stacks, queues, and DEQUES. Our chapter 1.6.1 is a stack. A stack is a collection of objects that are inserted and removed according to the last in, first out principle. A user may insert object into a stack at any time, but may only access or remove the most recently inserted object that remains at the so-called top of the stack. The name stack is derived from the metaphor of a stack of plate in a spring-loaded cafeteria plate dispenser. In this case, the fundamental operation involved the pushing and popping the plate on the stack. When we need a new plate from the dispenser, we pop the top plate of the stack, and when we add the plate, we push it down on the stack to become the new top plate. Perhaps an even more amusing example is here is a candy dispenser which stores mint candies in a spring-loaded container that pops out the topmost candy in the stack when the top of the dispenser is lifted, where we're going to see the figure 6.1. Stacks are a fundamental data structure. They are used in many applications, including the following. So guys, this is the figure 6.1. A systematic drawing of BEC. This is the silent dispenser of a mint candy. Chapter 6.1.1, the stack abstract data type. A stack is the simplest of all data structure, yet they are also among the most important. They are used in the host of different applications, such as tools for many more sophisticated data structure and algorithms. Formally, a stack is an abstract data type, or ADT, such as that instance S suppose the following two methods. The S that push, open and close parentheses, there is a small letter E, which is add element E to the top of stack S. And the other one is S that pop with the close and open parentheses. Remove and return the top element from the stack S. An error occurs if the stack is empty. Additionally, let us define the following accessor methods for convenience, which is the S that top, open and close parentheses, return a reference to the top element of the stack without removing it. An error occurs if the stack is empty. And the other one is S that S empty, close and open parentheses, return true if the stack S does not contain any elements. And len S, return the number of the element in stack S. In Python, we implement this with a special method. And this is the example 6.3.1, which is defined in the stack abstract data type. Next. Chapter 6.1.2, simply array-based stack implementation. We can implement a stack quite easily by storing its element in a Python list. The list class already supports adding an element at the end with the append method, and removing the last element with the pop method. So it is natural to align the top of the stack in the end of the list is shown in the figure 6.2, which is this is the figure 6.2. Chapter 6.1.3, reversing data using a stack. As a consequence of last in first out, or LIFO protocol, a stack can be used as a general tool to reverse the data sequence. For example, if the values 1, 2, and 3 are pushed onto a stack on the order, there will be popped from the stack on the order 3, 2, 1, 3, 2, and then 1. This idea can be applied in the variety of settings. For example, we might wish to print lines of the file reverse in order to display the data set in the decreasing order rather than increasing order. This can be accomplished by reading each line and pushed it onto a stack, and then writing a lines in the order they are popped. Chapter 6.1.4, Matching Parentheses in HTML Tags. We explored two related applications of stack, both of which involve testing for pairs of matching delimiters. In our first application, we consider arithmetic expression that may contain various pairs of grouping symbols such as parentheses, which is this one, and braces, curly braces, and a bracket. What? Each opening symbol must match its corresponding closing symbol. For example, a left bracket must match a corresponding right bracket. As an expression, the following example further illustrates to this concept. That's correct, and so on. Chapter 6.1, stacks again. We assume the input is a sequence of characters such as this equation or this example. We perform a left-to-right scan of the original sequence using a stack S to facilitate the matching of grouping symbols. Each time we encounter an opening symbol, we push the control onto S. In each time we encounter a closing symbol, we pop a symbol from the stack S, assuming S is not expression. It's not empty, rather. And check these two samples form of a valid pair. If we reach at the end of the expression and the stack is empty, then the original expression was properly matched. Otherwise, there must be an opening delimiter on the stack without a matching symbol. If the length of the original expression is n, the algorithm will make at the most n calls to push and n calls to pop. Those calls run in a total of O, in open parentheses, n time, even considering the amortized nature of the O open and close parentheses 1 time. Because for those methods, given that our selection of possible delimiters each run in 1 time, combining this operation, the match algorithm on the sequence of matching tags in a markup language. Another application of matching delimiters is in the validation of markup languages such as HTML or XML. HTML is the standard format of hyperlinked documents in the internet, and XML is an extendable markup language used for a variety of structured data sets. We show the sample of HTML in possible rendering figure 6.3. Example of stacks. We have a 5 example of stack, and this is the number 1. The cards. Second is our cups, like the PEZ candies. Number 3, ice cream. Number 4, the yellow pad, and the last is, what do you call this? I don't know what to call this. Yeah, that's it. And our chapter 6.2 is QUEUES. Another fundamental data structure is a queue. It is a close cousin of the stack, as a queue is a collection of objects that are inserted and removed according to the first in, first out, or FIFO principle. That is, element can be inserted at any time, but only the element that has been in the queue the longest can be next removed. We usually say the element entered in the queue at the back of and are removed from the front. The metaphor for this terminology is a line of people waiting to get on to get an amusement park's ride. People waiting for such a ride enter at the back of the line and get on the ride from the front of the line. What? Chapter 6.2, the Q abstract data type. The Q abstract data type, or ADT, abstract data type, supports the following two fundamental methods for a queue. The queue that in queue, open close parenthesis in, Q and DQ. Qn first and Q dot S empty and len dot Q. Chapter 6.2.2, array-based queue implementation. For the stack ADT, we create the very simple adapter class that uses a Python list as the underlying storage. It may be very tempting to use as a similar approach for supporting the queue ADT. We could in queue element E by calling append E to add it to the end of the list. We could use the syntax pop0 as opposed to pop blank to intentionally remove the first element from the list when dequeuing. We can improve on the above strategy by avoiding the call the pop0 entirely. We can replace the dequeue entire the array with a reference to none, and maintain the explicit variable f to store the index of the element that is currently at the front of the dequeue. Such an algorithm for dequeue would run in 0, 1 time after several dequeue operations. This is a figure 6.5, allowing the front of the dequeue of drift away from the index O. Using an array circularly and developing a more robust queue implementation, we allow the front of the queue to drift and we allow the contents of the queue to wrap around the end of the underlying array. We assume that our underlying array has fixed length and that is greater than the actual number of elements in the queue. New elements are in queue towards the end of the current queue, progressing from the front of index n-1 and continuing at index O, then 1. Figure 6.6 illustrates such a queue with first element E and last element N, which is this and this. Our example for queue is line for applying work. Number 2 is counter line. Number 3 is getting tickets for a concert. And then cars. Or ordering foods. And this is our last chapter 6.3, double-ended queues or DQs. We next consider the queue-like data structure that supports insertion and deletion at both of the front and the back of the queue, such as structure in called double-ended queue or DQ, which is usually pronounced DEQ to avoid confusion with the DQ method of the regular queue ADT, which is pronounced like an abbreviation D.Q. The DQ abstract data type is more general than both of the stack and the queue ADTs. The extra generality can be useful in some application. For example, we describe a restaurant using a queue to maintain the wait list. Occasionally, the first person might be removed from the queue only to find that the table was not available. Typically, the restaurant will reinsert the person at the first position in the queue. It may also be that a customer at the end of the queue may grow impatient and leave restaurant. Chapter 6.3.1, the DQ abstract data type. To provide a symmetrical abstraction, the DQ or DQ ADT is defined so that DQD supports the following methods, which is D dot add first, D dot add last, D dot delete first, and D dot delete last. Additionally, the DQADT will include the following assessor: the D dot first, the D dot last, D dot is empty, and len. Our chapter 6.3.2, implementing the DQ with the circular array. We can implement the DQADT in much the same way as the arrayQ class provided in code fragments 6.6 and 6.7 of section 6.2.2. We recommend maintaining the same three instance variables, data, size, and front. Whenever we need to know the index of the back of the DQ or the first available slot beyond the back of the DQ, we use modular arithmetic for the computation. Chapter 6.3.3, DQs in the Python collection modules. An implementation of a DQ class is available in Python's standard collection module. A summary of the most commonly used behavior of the collection DQ class is given in table 6.4. It uses more asymmetric nomenclature than our ADT. And thank you so much. See you again. Bye.